Welcome to the Explainer Strategists. I am absolutely thrilled to have you here. Listen, we are going full Top Gun today. We're talking advanced, high-stakes aerial combat tactics, but specifically designed for tackling the absolute toughest exam questions in your Cambridge 9618 computer science syllabus. Think of this session as your elite flight school, an exclusive, behind-the-scenes look straight into the Cambridge Examiner's playbook for Paper 2. Today, we are completely demystifying the process of writing low-level code with different addressing modes. Make no mistake, this right here, this is the danger zone. But it's also exactly where you can separate yourself from the pack and fly at maximum altitude. To set the stage, let's look at a real, highly complex past paper scenario. Imagine an exam paper sitting in front of you. I want to introduce you to two types of students we see crashing and burning every single year. First, there's Alex. Alex looks at a low-level code question, completely panics, and overloads the answer sheet with raw, unorganized computer science facts. Alex just dumps binary strings and textbook definitions hoping anything sticks, but offers zero actual analysis. Then we have Sam. Sam thinks they're a hotshot, rushes through the code, entirely misses the strict requirements of the command words, and just scribbles down a final hex value. We are going to look at their flawed answers, complete with the examiner's red pen marks, and we are going to break down the exact strategies you need to secure top marks and avoid the traps that shoot so many candidates down. Okay, let's fire up the engines and dive in.
Take a close look at this massive number on the screen. 15%. That is not a typo, and it's certainly not an exaggeration. Mastering low-level code and addressing modes accounts for roughly 15% of your total marks in Paper 2. That is a massive, grade-defining chunk of your final score sitting right here in this one single topic. To really put this into perspective, think back to Alex and Sam. When Alex just dumps facts without structure, or when Sam rushes and fails to show any logical working, they are literally leaving that entire 15% on the table. It's like flying a fighter jet without checking your instruments. The examiners are ruthless here. If you don't play by their specific rules, that 15% vanishes. Our mission today is to completely overhaul your approach so you do not make their fatal mistakes. We're going to turn those red pen marks into green check marks.
So, here is our tactical flight plan for today. First, we discovered the 15% challenge. Next up, we'll establish the theoretical foundations. Then, we'll map out the procedural framework. After that, evaluating algorithm quality. And we will finish strong with the top 3 examiner warnings.
Let's move into Sector 1. Theoretical foundations. We need to start thinking exactly like a Cambridge examiner.
If you genuinely want to ace Paper 2, you have to stop thinking like a stressed-out student trying to pass a test and start thinking like a Cambridge examiner who is assessing specific cognitive domains. The assessment objectives for writing low-level code target 3 distinct areas: your knowledge and understanding, your practical application, and your critical analysis. It is not just about knowing what an index addressing mode is, it's about proving you can decode the command words, apply the mode to a completely unfamiliar memory register, and analyze the outcome. And this brilliantly illustrates the core trap. Look at the comparison here. Superficial breadth versus analytical depth. This is exactly where our student Alex goes completely wrong. Alex provides superficial breadth, writing down everything they've ever memorized about immediate, direct, and indirect addressing, without actually solving the specific problem given in the scenario. The academic benchmarks for Cambridge 1698 require logical, structured reasoning. The assessment framework explicitly prioritizes analytical depth. Think of it like a laser focus rather than a floodlight. You need to identify the exact command word. Is it describe, evaluate, or trace? And then drill deep. Before we continue into the exact breakdown of how to structure your answers, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's get back to building that analytical depth.
Now, what's incredibly powerful about this next set of rules is that it's the exact formula for analytical depth. According to the principal examiner reports, the candidates who achieve significantly higher marks do 3 things consistently. First, precise definitions, no vague, wishy-washy language. Second, causal relationships. You have to explain why a specific addressing mode changes the value in the accumulator in a certain way. And third, cross-topic connections. You need to integrate this code with your knowledge of hardware, logic gates, or memory architecture. To execute this perfectly, you need to use the PEAL framework for your written answers. P-E-E-L. Point, evidence, explanation, link. State your point about the low-level code. Provide evidence from the provided trace table. Explain the causal relationship of the instruction, and link it back to the overarching system requirement in the question prompt. If our rushing student, Sam, had just slowed down and used the PEAL framework instead of just scribbling down a final hex value, We would literally see their marks transform from 0 to 100%. It's a total game changer.
All right, transitioning into Sector 2, the procedural framework. This is where we learn to systematically solve complex problems.
Listen closely, because algorithmic thinking in low-level code is completely 100% dependent on step-by-step decomposition. You absolutely cannot look at a block of assembly language and try to solve it all at once in your head. That is a guaranteed crash and burn. You need a systematic, repeatable process to break down the complexities. Let's look at the exact steps of this transformation. This right here is your computer science success blueprint. Step 1. Identify given information. What are the initial contents of the accumulator and the index register? Step 2. Break into logical steps. Go line by line through the assembly code. Step 3. Solve systematically. Update your trace table one instruction at a time. Do not skip ahead. Step 4. Check for reasonableness. Does the final output actually make sense within the context of the program's intended function? This deconstruct, solve, evaluate method is your ultimate defense mechanism. It prevents you from getting overwhelmed when Cambridge throws a completely unfamiliar wildcard context at you. By forcing yourself to write down the state of the registers after every single instruction, you transform a chaotic guess into a structured, indisputable proof. Imagine Alex and Sam applying this, taking 60 seconds to rewrite their messy answers using just these 4 steps. The clarity is immediate.
Practical application specifically requires rigorous data interpretation skills. In the exam hall, you are going to be staring at memory addresses written in raw binary or hexadecimal. You must be able to flawlessly extract data from those binary representations, perform the calculations, whether that's an arithmetic shift, a logical AND, or an addition, and then draw evidence-based conclusions about the state of the system. If an instruction says LDX15 and memory location 15 contains the binary for the number 8, your instinct must be to load that exact binary string into the index register, not the accumulator. Extract, calculate, conclude. That loop has to become muscle memory. It has to become second nature if you want those top marks.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, moving into Sector 3, evaluating algorithm quality. Let's see critical analysis in action.
Okay, welcome to our interactive workshop phase. You've written the code, or you've traced the code, now you have to evaluate it. Critical analysis is what literally separates the A-star students from the rest of the pack. When examiners ask you to evaluate an algorithm or a piece of low-level code, they are scanning your answer for specific metrics. Let's do a quick mental data scan challenge. Imagine a complex data table on your screen right now. You have 60 seconds to extract the core trend. What are you looking for? You are looking to discuss time complexity. How many clock cycles or instructions does this specific addressing mode require compared to another? You are looking for space complexity. Is this indirect addressing method saving memory space at the cost of processing speed? And critically, you must identify edge cases and their effect on performance. What happens if the index register points to a memory location outside the allocated array? If you can confidently articulate these trade-offs, you are demonstrating pure, top-tier analytical depth.
And this brings us to Challenge 2, Find the Flaw. This is a major trap you have to avoid. When you are asked to compare, say, immediate addressing with indexed addressing, you cannot just write a paragraph about immediate and then a separate paragraph about indexed. The examiner report is incredibly clear on this. Comparative analysis requires you to identify both similarities and differences using explicit connectives, words like whereas, conversely, similarly. And every single comparison must be backed by evidence from the provided scenario. Let's look at a flawed sample paragraph from our friend Alex. Alex writes, immediate addressing is fast, indirect addressing uses pointers. Can you spot the flaw? I'll tell you. The flaw is that there is no connective and no direct comparison of the same attribute. That scores 0 analysis marks. A top-tier examiner-approved answer says, immediate addressing is faster because it requires no memory fetch cycle, whereas indirect addressing is slower as it requires 2 separate memory accesses. Boom, maximum altitude. That's how it's done.
Now for Challenge 3, speed writing. Remembering all these different modes, direct, indirect, indexed, immediate, relative, can be incredibly daunting. Here is a brilliant memory hack straight from our source material. Use a visual story method to encode concepts. Don't just memorize dry textbook definitions, create a mental visual story.
For immediate addressing, imagine the instruction physically holding the data right in its hands. It's immediate, it's right there. For indirect addressing, imagine going to a locker, opening it, and inside is just a map to another locker where the actual prize is. By giving these abstract computer science concepts a visual narrative, your brain encodes them so much faster. Under the intense pressure of a timed exam, that visual story will pop into your head instantly. If I gave you a 30-second timer right now to write one perfect PLEL paragraph on indirect addressing, those of you using the locker visual would crush it twice as fast as someone trying to recall a textbook definition.
Sector 4. Top 3 Examiner Warnings. Listen up, because this is about saving your hard-earned marks.
We are officially entering the final phase of our mission. It's time to talk about threat detection. We've analyzed the absolute latest principal examiner reports for Cambridge 9618, and we've isolated the exact areas where candidates are getting shot down and losing massive amounts of marks. So I pose this question to you. Where do you think most students lose these easy marks? Is it because the binary math is just too hard? Is it because the logic gates are too complex? No, absolutely not. It is almost always a failure of process. It's skipping steps. It's the difference between knowing the theory and applying the discipline to execute it under pressure. Let's look at the top 3 specific pitfalls you need to avoid.
Here they are, straight from the chief examiners. Number 1, forgetting to check for overflow and edge cases in low-level code calculations. If you add 2 binary numbers in an 8-bit register and the result is 9 bits, that overflow bit is absolutely critical. Students just ignore it, write down 8 bits, and lose the mark. Number 2, forgetting to check boundary conditions. If an index register is looping through an array of 10 items, what happens on the 11th iteration? You have to trace it to the very end to prove to the examiner you understand the boundary. And number 3, the biggest offense of all. Answers lack specific question context. Rote memorization completely fails here. If the question is about a temperature sensor using low-level code, and your answer is just a generic definition of addressing modes without ever mentioning the word temperature, sensor, or the specific memory addresses provided in the prompt, you will not get the application marks. You must tailor every single word to the exact scenario on the page.
And that leads us to the ultimate golden rule, your absolute safety net. Even if your final answer is wrong, method marks can save you. Examiner alert, students lose marks by not showing their working. If you trace 15 lines of assembly code and make one tiny, silly addition error on line 12, your final accumulator value is going to be wrong. If all you wrote down was that final wrong value, exactly like our rushing student Sam usually does, you get 0 marks. But if you meticulously filled out the trace table step by step, showing you're working for lines 1 through 11, the examiner will award you almost all the method marks. Show you're working every single time. Do not let those marks slip away.
Let's bring it all together into your ultimate cheat sheet. The entire methodology for mastering low-level code in addressing modes comes down to 3 powerful words. Deconstruct. Break the complex code into logical, individual instructions. Solve. Process each instruction systematically, applying precise definitions and showing you're working. Evaluate. Analyze the time complexity, space complexity, and context-specific performance using comparative connectives. If you follow the 3 rules that guarantee top marks, command word decoding, Peel framework application, and a strict time management matrix, you will unlock 100% of your mark potential. That is your complete computer science answering system.
I want to leave you with a final thought to really mull over. Knowledge is only potential power until it's actively applied. How will you apply the visual story method to your very next past paper question? The next time you see indirect addressing, are you going to freeze? Or are you going to picture that locker and map, confidently deconstruct the code, and secure every single available method mark? Students who consistently implement these computer science strategies see an average improvement of 2 full grade boundaries. But that only happens if you practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at @acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing right now. Our team responds to every single comment. Like and share this video with your study partner. Ace the Exams, your Cambridge success starts here. Thank you for joining me. Keep flying high, and I'll see you in the next masterclass.